Okay, welcome. So today we need to continue our discussion about uh, quotient spaces. And actually, we are going to get to introduce the quotient topology. So last time, let's go with a brief refresh. Mostly, what we did was first, you can always define the quotient of a quotient set under equivalence relation, under an equivalence relation. So this is what denoted by X quotient equivalence, which is by definition the collection of all equivalence classes. And remember here the equivalence class of a point X is, well, it's the subset of X, namely it's all points which are related to your given X. So this is very important. We have the quotient set, but it's not that useful if we don't consider the quotient map. Quotient map. Most of the time, I'm going to denote it by pi. It's a map going out of X to the quotient, which is given by, well, pi of X is going to be the class of X. So of course, this map is going to be subjective because in the quotient set, everything is a class. That's by definition. And then 3, this was our very important theorem. If you want to define functions out of the quotient space, so functions going out of the quotient space into any set, they come from functions out of X to Y, which descend to the quotient, so which are constant on equivalence classes. And the idea here is if you have a function f and you want to define this f bar, then f bar on the class of the point X, on a generic element of the quotient, is just going to be f at X, which is also f at any other element in the equivalence class of X, because we're assuming f is constant on classes. So that's how you define functions. Important thing is, so how do, once again, to define f bar, need the following: x raised to y implies f of x equals f of y. That's what we mean by f being constant on equivalence classes. Then we also said that the image of f bar is just the image set of f. And lastly, in case not only x equals y implies f of x equals f of y, but moreover, that's an if and only if, then f is injected. F bar is injected. So this is mostly what we did. And we also said that today, what we need to do was how do we use topology on X to get topology on the quotient. So that's what I need to do today. Okay, so the class today is going to start just with the definition of how do you do such thing, and then I will convince you why it makes sense. So today we're going to start with our definition slash theorem. Let's call this definition slash theorem 1. Let's take a topological space now. So X comma T. Okay, and let's assume we have an equivalence relation. So let's fill the mean equivalence relation on X. I'm going to try to define the topology of the quotient, but for that, I will really need my quotient map. So let's grab it here. Let's apply from X to the quotient with the quotient map. So everything here is set up. And here's the theorem part. Then the collection. So I'm going to denote this by T sub tilde. It's not a very common notation. This is going to include all subsets in the quotient set such that the preimage under the quotient map is open in X. So once again, I'm considering subsets of the quotient set for which the preimage under my very important quotient map is open in X. So I'm using the topology of X, of course. Then the claim is that this defines a topology on the quotient space. And the definition part is that it's called the quotient topology. So of course, quotient topology will not depend just on the relation or the set. It will also depend on one topology you're considering on X. Okay. So the setup, once again, we have a topological space with an equivalence relation, and we want to prove, well, need to show the three axioms of a topology. We need to show or to verify the three axioms. Maybe let's call this topology axioms. And what I mean is I need to show T tilde satisfies these things. So the first axiom, remember, was empty set lives in the topology. And that's just because, so now we need to remember what are the sets here? Well, exactly those for which the preimage is open. So if I'm claiming that the empty set lives in T tilde, I need to say something about the preimage of the empty set. The preimage of the empty set is just the empty set, which is open in X. Because, well, we have a topology, and the topology of X satisfies this axiom. Then second part of first axiom, the entire quotient space lives in the topology because the preimage of the quotient map is just going to be the entire domain, which is also open. So very formally, our T tilde will satisfy the first axiom. Second axiom, this is about, let's say, arbitrary unions first. So let's take a collection of sets all in our T tilde. And we want to show that the union is also a T tilde. So how do we show that? Well, we need to compute the preimage under U, under pi, sorry. So let's say that since all the i's are in T tilde, then what that means is, by definition of T tilde, the preimage is an element in T, is open in X. And now we use that T is a topology on X. It's closed under arbitrary unions. So T is closed under unions. Under unions, when we compute preimage of my union here, well, we know that's just union of preimages. And we're saying each of these guys lives in T, so also the union lives in T because T is closed under unions. And by definition of the tilde, that means that the set here also lives in T tilde because the preimage under phi lives in T. Okay, that's the second axiom. Third one, let's take V1 and V2, T tilde, only two of those. And I want to show, their intersection lives in T tilde. And this means the preimage of the intersection lives in T. That's the definition of T tilde. But now we compute the preimage of the intersection. Well, we know preimages behave well with intersections. So this is preimage of V1, intersection, preimage of V2. And this guy lives in T. Second one lives in T because V1 and V2 live in T tilde. So the preimage lives in T by definition of T tilde. This guy also lives in T because T is a topology. That means V1 intersection V2 lives in T tilde. And we verified very quickly the three axioms for a topology. So in other words, let's write the slogan here. So the slogan is the subset of the quotient space is open by definition if and only if the preimage under the quotient map is open in X. So that's the slogan for the quotient topology. So as you might see here, the quotient map plays a crucial role. Well, how crucial it is, and starting to get into this direction of justifying how natural the quotient topology is, here's our second theorem. And after this, we'll do some examples. So let's go to our setup. So let's assume we have an equivalence relation on a topological space. And let's say topological space is called X comma T. Then the claim here is that the quotient topology is the finest topology on the quotient set for which the quotient map such that the quotient map is continuous. And this is somehow an argument about why the quotient topology is a natural thing to consider. So the quotient is not just the set, it's also the map. Oops, sorry, this is wrong. Quotient map goes the other way around from X to the quotient. And let's prove this. So the proof will have two parts because we're saying the quotient topology is the finest doing something. So first we need to verify it does something, and then that is finer than any other topology doing that something. So part one is we need to show that if you consider the quotient topology on the quotient set, then the quotient map is continuous for this topology. Okay, so this is what I want to show. Maybe I'd say what. How do we prove this? Well, we need to take an open set in the codomain here. So let's call it B in T tilde. I want to show the preimage under phi is open in X. I want to show that phi is continuous, the preimage under phi of B inside of X is open. Well, that's by definition of T tilde. That's automatic. That is automatic by definition of T tilde. Namely, if T lives there, then the preimage is open in X. It's an element in T. That's how we define T tilde. So part one is done. Now part two here is what we need to do is assume that we have some topology T tilde on the quotient set is such that the quotient map phi from X with its topology to the quotient set with this new topology that we already know is continuous. So we need to assume that, and what we want to prove that that T quotient is finer than T prime. So what we want is this new T prime is inside the quotient topology. So how do we prove that? Well, element chasing. Let's take some, let's call it U in T prime. I want to show U is also an element in T tilde. Now, what can we do? Well, the only thing that we can use is that phi is continuous. Since phi is continuous landing into T prime, this phi is continuous. With this topology here, what we get that the preimage under phi of this U needs to live in T. Well, but then U is a subset of the quotient space for which the preimage is an element of T. So by definition of T tilde of the quotient topology, this means that U lives in the quotient topology because its preimage under T is open in X, is an element of T. So we've taken any element in T prime, show it lives in T tilde, and that means that T prime is a subset of T tilde, which means T tilde is finer than T prime, and that's any T prime, so T tilde is finer than any topology for which the quotient map is continuous, and that's exactly what we want. So this is a rather convincing argument or a very good reason about how natural this topology is. Okay, now we know we have a topology, we have a theorem stating how natural it is. Next thing we want to do is we want to understand this topology on examples. So then write what we want. What we want next is some examples as topological spaces of X quotient out by a relation. And now, if we want to understand these examples, we like to identify them with things that we already know. So the actually one is we want homomorphisms between quotient spaces and some spaces that we hopefully know. In other words, we want to identify these new things as things that we already understand. So the only way for us to do that is with our theorem about functions going out of quotients. So this is the next result. Theorem 3. Now let's take a map between topological spaces. from x to y, and we assume we have a relation on x, an equivalence relation on x, and assume also that f descends to the quotient and give us a map f bar from the quotient space to y. So this means, remember the definition says, if x is related to y, then f of x equals f of y. In such case, f will give you a function going out the quotient. Okay, then in this scenario, the following will hold. So notice I'm not assuming my f is continuous. The first statement is f is continuous if and only if f bar is continuous. And of course, on the quotient space, on the quotient set, I'm considering the quotient topology. The second part is that if our F happens to be open, and remember that means F maps open sets to open sets. So if F is open, so is F bar. So it's okay. So this is going to be very helpful for us. Let's prove this theorem. Let's go with one. So one, we have two directions. Usually we'll go with the forward one first, but in this case, the backwards implication is going to be easier. So let's assume first f bar is continuous. And here we like to prove that f is continuous. But the important thing about f bar, remember this is sometimes read as f factors to the quotient. So f is first go to the quotient and then do f bar. So f is this composition. Now, we know that the quotient map is continuous. So if we assume f bar is continuous, the composition will also be continuous. So let's write that. Since f is a composition of continuous maps, it needs to be continuous. Composition of continuous maps. Then f is continuous. So not much to be done here. Now the thing is, for the other direction, here we assume f is continuous. And the thing is, we cannot deduce from that equation that f bar is continuous because, well, you cannot like cancel phi and put it here with its inverse. So we need to do something else. And the something else is we just go by definition. And so that's what we assume, and we want to show f bar is also going to be continuous. So how do we prove such thing? We need to take an open set in Y. So let's U inside of Y open. I want to show the preimage under F bar of U, which is a subset of the quotient, is open. And it's open, of course, in the quotient topology. So how do we show that? So by definition of the quotient topology, This just means some subset of the quotient is open is if, so I'm applying the definition to this set. That just means you apply the preimage under phi of whatever set you have. In this case, this is the set we have. So that's our set. We want this to be open in X. But now this is good things, since this is good news. Since F is F field decomposed with phi, then, well, the preimage of the preimage, that's the same as the preimage of the composition, but on the other direction. But the composition is just F. So this is the preimage of the F. And we know F is open. So since F is open, sorry, continuous, and Y is open in Y, so U is open in Y, F is continuous, we know that the preimage F inverse of U is open in X. Well, that means that the inverse of F bar inverse of U is open in X. And by definition of the quotient topology, this set inside the quotient set is open. This is definition of the quotient topology. And U is an arbitrary open set in Y, so F bar is good. Okay, that's exactly what I want to prove. Very instructive. And for the second thing here, that's just going to be a combo assignment, and the ideas are very similar. So I will leave it to you. We can only prove one direction, and we come back to why that's the case later on. Okay, so we're finally ready to do some examples, or to do at least one example. So let's take a simplified version of the example we did last time. Well, actually, it's another version. It's a brand new example. Let's take the the Euclidean plane. So X is going to be R2 with standard topology. So for this standard topology, you can take any metric on R2, for example, the Euclidean metric that we call B2. You can also take the infinity topology. That's going to give you basic sets as rectangles. And these topologies are the same, so we're safe with it. We're going to define a relation. That's the second thing we need on our X by the following rule. A pair X1, X2 is going to be related to a pair Y1, Y2. You can only, well, X1 squared plus X2 squared equals Y1 squared plus Y2 squared. So whether these quantities here, the first quantity over here, that's just the distance from to this point to the origin. And this quantity is the distance from this point to the origin. So that's the only thing that we're saying. So we're relating points with the same distance to the origin. Are related. Now, to be completely honest, the distance is the square root of this quantity, and I will like explain that in a second. But that's essentially what's going on. Now, that being the case, if we're identifying all points with the same distance, the set of equivalence classes under this relation is going to be, remember the equivalence classes, what they do is you take a point X, you compute its class, and what's going to be the class of a point X? Well, it's going to be exactly all other points which have the same distance to the origin. So the set of equivalence classes under this relation is going to be, well, circles centered at the origin. And here the radius can be anything. And I also want to consider the circle with radius 0, but usually that's not called a circle, so let's just say the equivalence class of 0, which is 0 itself. And now my claim is there is a homeomorphism So remember that means homeomorphism. That means bijective continuous function for which the inverse is also continuous. So there is a homeomorphism from the quotient to, well, I'm just saying you only need to give me a real number which is non-negative, but I'm going to prove the quotient space is just this semi-infinite. Okay, how do we prove that? Well, step zero here is we're going to define a map. Instead of going out of the quotient set, going out of X. So from X, which is R2, to semi-open interval, let's call this map F, and it's going to be given by F at an element in X, so X1, X2 is going to be kind of this quantity, but I want to take the square root because that's actually the distance to the origin. So it's going to be square root of X1 squared plus X2 squared. And this is what's denoted as the norm. So if this is called X, this is the norm of X. Just the distance to the origin. Okay. That's our map. And now I want to claim that this map is going to give us the homeomorphism that we're trying to find. It's going to be F tilde, F bar. So here's how we need to argue this. Notice the following. First thing, I want to prove that F descends to the quotient. So if you take 2 points, X1, X2, which is related to Y1, Y2, then that means that X1 squared plus X2 squared is Y1 squared plus Y2 squared. That's the definition of my relation. Now, if that's the case, you take square roots, then you still have the same equality. So f of X1, X2 equals f of Y1, Y2. And that means that f descends to the quotients. So our f descends to a map. We're going to call it f bar from the quotient to 0. If. Okay. What about this f bar map? Well, it's given by the following rule. F bar at a class of X1, X2 is just going to be f at X1, X2. And this is well defined because f is constant on equivalence classes. That's what we proved. So we have a map. Part 2 is this map happens to be injected. And remember, we have a criterion for this. This is what we did last time and also refreshed today very beginning. So why is F injective? F bar, sorry. Well, that's because if F collapses 2 points, x1, x2 with y1, y2, then also when you take square roots, we're going to have the same. So if you call this x and this y, then the norm of x is going to be the norm of y. That's the definition. So also x1, x2 is related to y1, y2. And by our theorem, F is injected, F bar is injected. Okay, so far there's no topology involved. It's going to continue like that for this point. We're going to notice F bar is surjective. Well, remember the image of F bar is exactly the image of F. And our F is, of course, when we go up to our F, this is our F. Since we're considering this set here, it is going to be surjective. Anything here is the norm of some point in R2. So F is surjective because so is it. So surjectivity, injectivity means we have a bijective function, F bar. Now, furthermore, our F bar is continuous. Now, to prove this, we only need to prove that the function f is continuous. That's the theorem we just proved. In fact, f going out of R2 to R given by x1, x2 goes to x1 squared. Maybe let's do square roots. X1 squared plus x2 squared. This map is continuous. So it's going to be continuous when you co-restrict the codomain to zero infinite within this topology, and we're done. So let's say we know this from analysis. Okay, we have this function f bar, which is a continuous bijection. It's still not enough. We want to prove it's a homomorphism. And we know the only thing that remains to be proven is that f bar is open. That's equivalent to the inverse being continuous. So to prove that f bar is open, once again, that's the second point of our last theorem. So to prove this, we just need to prove that f is open. So f, which goes from R2 to zero infinite, is open. That's the second part of our theorem from before, the last theorem. Okay, that's what we need to prove. Remember, a function being open means you take any open set in the domain, then it's going to be mapped into an open set of the codomain. But by homework assignment, we know that we only need to prove, instead of proving that any open set is going to be mapped into an open set, only need to prove that basic sets are going to be mapped to open. So prove that f of an arbitrary null x comma epsilon is open. And this for every is open, sorry, for every x in R2 and epsilon positive real. Okay, how do we prove this? Well, this is going to be a consequence of the following. So this follows from the following that I'm not going to prove, but it's very easy to verify. It's just a set equality. If you compute f of a ball, so remember, f at a circle is just going to take every point in the circle to the radius of that circle. Maybe let's use radius here instead of epsilon. Sorry, let me change this because I don't want you to think that epsilon is small. Epsilon can be anything. So r, radius. So what f is doing is, if you take inside the ball many concentric circles, each circle will just go to the number. So the ball, since it's open, it's going to be mapped either into an open interval. So the open interval is going to be norm of x minus r, norm of x plus r. But that's only going to be the case if the norm is big enough. And otherwise, remember, f only takes non-negative values. So we shouldn't expect this if that's not true. So this is for x bigger than or equal to r. And it's going to be 0 radius plus r, so same right extreme, otherwise, namely if norm of x is more than r. But in any case, the ball is going to be mapped into something else. Hence, f is open. And by our theorem, also is f bar. And now, using all these things, we have a function f bar going out the quotient to the semi-infinite interval, which is given by f of the class of x, f bar of the class of x equals the norm of x, is a homeomorphism. We just proved it's bijective, it's continuous, and it's inverse. And it's open, so it's inverse, it's also continuous. So what we just did is we identified our quotient space as an open interval. And now let me finish this with a picture of what we just did. Didn't want to give you this before because I don't want to be to abuse my drawings. But what's happening here is that's our x. So what we're doing is this is our x. Here is the real line. I'm going to use it to use a vertical line. So what we're doing is we have a function f that at each circle, so if this is a circle of radius r, then the function is taking that entire circle to r. Any point in that circle is going to land in r. And of course, then I'm only going to take non-negative values. So I'm going to start at 0 and go to r. So this is what f is doing. Maybe I use another color. This is what f is doing. Here you have r prime. Here's your f. F is constant on equivalence classes. That means you have a function on the quotient, and what we prove is the function on the quotient is a homeomorphism. So this is our first example when we can identify a quotient space as something that we know using all our theorems. So that's it for today. Next time, we'll also continue discussing quotients and how we can identify them with something that we already know.